Okay, yeah, I'll keep it short. It's kind of a continuation of, I guess, the talk I gave this morning. So yeah, I was talking about in the morning. I was telling you about this semi-random model, and trying to find large clicks in it. So this question is so. It's, by the way, it's not my question. It's a question that Uri Feige asked, just like the question I was talking about in the morning. This is also one of his questions, and the main motivation is like in some sense, how far can we push the average case model and get algorithms that wildly beat the kind of guarantees that are really impossible to get as far as we know in the worst case, right? Like somehow how close can we get to the worst case while still somehow getting better algorithms. So it's a very concrete model Feige proposes. Suppose you start from a worst case graph G. Okay, so this could be like, I don't know, whatever graph you can start with. But now introduce a click as follows. You choose a uniformly random set S of k vertices and complete the click on them. Okay, the goal is, given such a graph, to find okay, so I wrote finding S here. That doesn't make sense. The right thing should have been design a polynomial time algorithm for finding a k click in the resulting graph. Okay, and the key thing to notice is that if the choice of this planted k click was not done randomly, so if I just like introduce a k click on like some subset S of vertices adversarially chosen, then this would be the worst case k click problem. Okay, so somehow the only benignness in this model, the only thing that could potentially make it easier than the worst case click problem is the fact that I introduced a k click on a uniformly random set of k vertices. The question is, does this really make it easier? Is there a polynomial time algorithm that could find a k click in this graph for some non-trivially small k? And what non-trivial would mean? Let me give you some intuition about it. In the worst case, even when a graph is promised to contain a click of size n over 3, so like a very, very large click, the best that we know an algorithm can do is find like a click of size n to the epsilon for some small constant epsilon. Okay, so even when there is a linear size click in the graph, the problem doesn't get easier in the worst case. So even if you give me an algorithm here that works for k, which is like alpha n for like some small constant alpha, it would be very interesting. Okay, so and yeah, I guess so Feige didn't add this interpretation because I think that's his style. He doesn't usually like philosophize unlike me, so let me philosophize for him. I think the way I would interpret a algorithm, if it does exist, is somehow that maybe in a very strong sense, the worst case hardness of click really somehow maybe doesn't matter as much, right? Like somehow we are saying that even with this very small amount of randomness, this very small restriction that the adversary cannot really like make a designer cut around the planted click, that's already like somehow enough to make the problem significantly easier. So if that does turn out to be the conclusion, I think it's a very powerful statement about whether the click problem is hard to begin with. So yeah, that's my problem.
Thanks, Pravesh. Next, we have Roy for his problem.
Hi, everyone. Okay, so I'm about to give a talk, so this might make more sense after my talk. So I'll use it as a chance to advertise my talk. So you now have to stay till 5:15 if you want to know what I'm talking about. Okay, so the problem that I want to propose is a variant of what I'm calling random order covering IPs. So this is a covering IP. Okay, there's a cost function C. I'm minimizing like C transpose X subject to the constraint that AI transpose X is bigger than 1 and X is integral. Okay, and okay, so that's a covering IP, and by the random order version, I mean that okay, so an adversary like fixes this this IP beforehand, but we don't know it, and then the adversary rolls some dice and then reveals the constraints in a uniformly random order. Okay, so maybe it looks like, sorry for the jumps, like this, and the goal is to maintain a solution to this IP, excuse me. But the hard part is that the X that you maintain needs to be monotonically increasing. So if you increase the coordinate, like it always helps to increase a coordinate in terms of feasibility, it hurts you in cost, and you're not allowed to like decrease once you've increased, okay? And set cover is the special case when the constraint matrix is all 0, 1. Okay, does this setup make sense? So what I'm going to talk about in my talk, and I forgot to write this on the slides. I'll write it here. So in adversarial order, I think it works.
Quite good.
Good, right? So in adversarial order, if you don't have this like randomness, basically the right answer is log squared n, and here n is like poly m is let's say poly of what I'm calling the aspect ratio. So all the parameters of the problem are like polynomially related. This thing is like you know, a max over a min, some like, oh, sorry for the bad handwriting, some measure of like how well conditioned the matrix is. Okay, so all these things are sort of like the same within the log, and basically in adversarial order, you need to lose a log squared, and we know how to do this. This is in the competitive ratio. In random order, if you come to my talk, which you should, you can improve this to a single log. Okay, and the question, so this I remembered to write in the slides. The open question I want to propose is, what if you have box constraints on this IP? So I add this constraint that every coordinate of x must be at most 1. Now what's the answer? Is it log squared or a single log? So that's the open question. And I'm sorry that there's not enough context. Yeah, please stay for my talk and you'll see the context. Thanks. I can't hear. Oh, so if you look at the fractional, you want to look at the fractional version? Yeah, then in adversarial order you can get a log, and in random order that's a lower bound as well. So there's kind of no question to be asked. Yeah. Right. Yeah. So okay, so what I mean, sorry, you're gonna see the like more setup sort of in the talk. You sort of at the end of this game, you get some solution. And I'm comparing like the cost you have at the end of this game when you're constrained to be monotonically increasing, you're comparing yourself to like if you had full information and infinite computing power. Okay, so we're measuring the ratio between these things. That's what I meant by logs, by the logs earlier. Make sense? Yeah. Yeah, so you know the box constraints ahead of time. Yeah. Yeah. Sorry, go ahead. My bad. I promise you it's feasible. Yeah, everything is like. I don't think so. Yo, sorry, A is non-negative. I'm sorry, yeah. The A here is, yeah. Yeah. Sorry, that's important. Yeah. Any more questions? Yeah, so in the adversarial model, there's like somewhat standard tricks for dealing with this type of thing, and none of them work here. So have at it. Okay, thank you.
Okay, hello everyone. Yeah, my name is Sahil. So I'll say a few open problems related to this field or problem of profit inequality. So the classic problem is like an optimal shopping problem from like 40, 50 years ago. But there have been like lots of generalizations of this problem that have been studied. And so I'll like very briefly mention some of the problems. So the setting is the following, the classical setting at least. You have n known distributions, n random variables. You know their distributions, they are all independent random variables, but you don't know the realizations. So think of them as like n boxes, which are all closed. Each box has a reward, where the reward of the ith box is from some known distribution. So xi is some random variable. You'll get to see the outcomes or like the realizations of these random variables one by one in the sequence x1, x2, x3, and so on. As soon as you get to see a value of a random variable, you have to immediately decide, are you accepting it or not? So in the most classical setting, you are only allowed to accept one of the random variables, and your goal is to maximize the value that you collect. So for instance, if you have these 4 random variables, maybe first you see the realization of x1, it's 4. you need to immediately decide, are you taking this value 4 or are you rejecting it? If you reject, it's gone. If you take it, then you that's the reward that you get. So you cannot drop it later. But maybe you decide to continue, x2 is equal 6, and at some point you decide to just stop and take the x2 equals 6. But had you continued, maybe x4 was larger and so on. So the question is, what's the largest value you can get? Good. So, and this problem, as I was saying, like it has lots and lots of applications. It picked up a lot in the last 2 decades in TCS, mainly because of applications in mechanism design and online algorithms. There are generalizations of this problem where rather than selecting a single random variable, you are selecting a subset of them. And your goal is to maximize the sum of their values. For instance, you want to select k of them and you want to maximize the sum of those k values. Or you could have like some packing constraint on these random variables. You can only select a subset of random variables as long as they are feasible inside your packing constraint, like a matching constraint or a matroid constraint. There are 2 common benchmarks that people study for this problem. One is the hindsight optimum, which is just look at the realizations of these random variables offline and take the largest possible feasible set, or like the largest possible single element if you're in the single item selection problem. So that's the hindsight optimum, and look at the expected value of this. And the question becomes more of a competitive ratio kind of a question that, okay, what fraction of this hindsight optimum can you get? That's one thing that people study. The other common benchmark is the optimal online policy, which is you view this problem as an MDP, and among all possible policies, what's the largest value you can get? And like the challenges are a bit different because the first setting, it's more of an information theoretic challenge, like how close can I get to the hindsight optimum? Whereas in the second one, it's more of a computational challenge because if I give you infinite computational power, you could just solve the MDP. So just to give a little more intuition, so why maybe say hindsight optimum? For example, here is a setting where you cannot achieve the hindsight optimum and you have to lose a factor of 2 even for single item selection problem, like single random variable selection problem. And this is an example where you just have 2 random variables. X1 always takes value 1. X2 takes a large value of 1 over epsilon with small probability epsilon, and otherwise it's 0. It's easy to see here that the expected max or the hindsight optimum is close to 2. It's roughly like 2 minus epsilon. Whereas any online policy, either it takes the first variable and gets a value of 1, or it rejects it and goes to the second one, which again, in expectation only gives you a value of 1. So the ratio is roughly at 2. And actually, this is the classical theorem which goes back to at least like Krengel, Suxton, Garling from the 70s, that there exists an online algorithm which gets you at least half of the expected max. So this is the classical result for the single item selection problem. And people have been working on its generalizations for multiple items. On the other side, if you compare yourself to the optimal online policy, then actually for the single item, there's a simple dynamic program you can run. Like basically, you will always select the last element. The second last element, I'll select it if its realization is more than the expected value of the last element, and so on. So I can solve such kind of a dynamic program from the end, and that gives me the optimal policy, at least for the single item selection problem. So single item problem is kind of well understood because this half factor is tight. Moreover, in the optimal online policy, you can get the factor 1, basically, you can get the optimal policy. And here's a table of open problems. So yeah. So let me just outline. So first, let's look at the hindsight optimum benchmark. So as I was saying, for single item, half is known. This is the result of Krengel, Suxton, Garling. There was a result of Bobby Kleinberg and Matt Weinberg, which showed that even for matroids, like if you have to select a subset of random variables, which have to be independent in a matroid, in a given matroid, and you want to maximize their sum, then also you can get a half approximation, which is tight. For matchings also, it's known that half is tight. The open questions here are of the form that what if I don't, for instance, one open question is what if I don't know the distributions, I only give you a few samples from these distributions, maybe even like a single sample or a constant number of samples from each of the distributions. Can I still get a constant ratio with respect to the hindsight optimum, expected hindsight optimum? So that's one open question. There are also open questions for general arbitrary packing constraints, like even if I go beyond matroids, like even arbitrary independent set, or like you can imagine any like intersection of arbitrary number of matroids or any such packing constraint. There's a gap of between log square and single log, like log n over log log. There are a bunch of questions in the optimal online policy benchmark as well. So for single item, although you can get the optimal policy, the simple dynamic program gives you. For matroids, we don't know much. In fact, I mean, is it possible to even get anything better than half? We don't know. Notice any result that I get with respect to the hindsight optimum, that same comparative ratio also automatically carries over to the optimal online policy as well, because that benchmark is only smaller. But we don't know anything better than half. Similarly, yeah, so I mean, there are like a few, for matchings, we know better than half. We know like a 1 minus 1 over E, but we don't know again the best constants. There are many other open problems in this area as well. For instance, what if I consider other variants where, so one variant that has been studied is the free order variant of these problems. So currently I assume that in these random variables, the arrival order is given to you, like it's chosen by an adversary. You only get to see their outcomes in the sequence x1, x2, x3, and so on. But what if I also allow you to change the order? Like maybe your algorithm knows the distribution and it can decide, okay, maybe show me x5 first. Depending on the outcome, I might go to some other random variable and so on. So that again introduces a bunch of open problems already for single item. For instance, there's one beautiful question I like. So what we don't know is that for the single item selection in this free order model, it's not clear if this problem is any harder than the IID case. By IID, I mean like all the random variables have exactly the same distribution. So in this special case of IID, it's known that you can get some comparative ratio of roughly 0.74. And so it's plausible that even for free order model, you can get such a ratio. Again, there are a bunch of open questions for matroids, matchings, and even like, and compared to the optimal online policy, single item, you can get, it's known that you can get an EP task, but FP task is unknown. And there are a bunch of other questions as well. Yeah, so let me conclude here.
So I'll now talk about one problem that I worked on a couple of years back. So this is the online metric matching problem. So here it's a matching problem, bipartite matching problem. There are n servers. So the servers are indicated like servers here. And the clients arrive online. So there are n servers and n clients. But the thing is, there is a metric space between all the two n vertices. So there's a big metric space. So there's no infinite distance and so on. So all distances are finite and satisfy the triangle inequality. Okay. So the goal is the clients arrive online, and when a client arrives, so let me try to switch on. Okay. So when the client arrives, the algorithm must actually match a client to a free server at this point. Okay, so this is the problem. So in this example, you may match this to a free server, so being the closest. And the matching must be immediate, so it must be when the client arrives, and irrevocable. So this is the classical online matching problem. So you can't change your decisions once you commit to them. So the second client arrives, and then you match it to a free server. Then a third client arrives. And even though the server closest to it is, I mean, unfortunately, the server closest to it is booked, so we have to match it to a further away server. So the cost of the online algorithm is the sum of these distances in your matching. Recall that it's a metric space. And the competitive ratio of an algorithm is this algorithm's cost upon the optimal cost, which is a hindsight optimal perfect matching that you can find in this instance. So it's a complete bipartite graph, and you can find a perfect matching. So what is known? So the known is in the randomized world. So I think these are the latest. Maybe if someone knows of more better results, let me know. But what is known is for the in the randomized algorithms, I think we know log squared and competitive randomized algorithms. And in deterministic, we know roughly 2n competitive deterministic algorithm for this problem. Okay, so that's the lay of the land. I think the lower bound in randomized is also omega of log n. So there's a gap there, which is an open question already. So what I worked on a few years back is the problem where you are allowed some recourse where you can change the past decisions subsequently. Okay, so what's known there? So what's known? I mean, just to formalize the problem, right? So when a new client arrives, the algorithm can change a past matching, and we keep track of how many changes we have done over time. And if that is small, then the recourse of the algorithm is said to be small. So in this case, what we can do is we can reassign the second client to a free server and then match the third client to this free server now. So the cost has come down, but we've incurred a recourse of 1. So the goal is with, say, a constant amortized recourse, which means a total of n swaps over n arrivals or order n swaps over n arrivals, what's the competitive ratio we can maintain here? So a few of you in the audience I know have worked on this problem or variants of this, so they may know the results already, but it's an interesting question for the others if you don't know. So it's a clean question and there are lots of open questions here. So there's a very simple algorithm which you can do to get a order log n competitive deterministic algorithm with a small amount of recourse. So with order log n recourse. So it's a very simple algorithm and it already improves. So in the model without recourse, the best, I mean, the deterministic algorithm landscape is linear competitive ratio, and you can already get log n competitive ratio with log n recourse. But again, this is the best we know so far. So can we do better? Constant competitive with constant recourse is something we don't know, for example. So that's open, even randomized, deterministic or randomized. So that's the first natural open question here. Sorry, any? Yeah. So we don't know lower bounds also. So the model with recourse, again, we don't know any lower bounds here. And the third is, even for metrics being a special case, we don't know too much better. So for example, is a metric as an line. So can we do like constant? We don't know that. So even trivial metrics, I don't think we know too much. And the fourth is, maybe there's maybe you can assume distributional properties about the arrival. So maybe the clients are sampled IID from the same distribution. So even there, I think we don't know constants. So lots of questions here, and we have very few answers. So that's the landscape I wanted to propose. Any questions?
Okay. So the question is, as mentioned earlier, so on Metroids we do achieve a half competitive ratio in the for the profit problem. So let me add some more information to this. So if your Metroid is k uniform, what does that mean? You are allowed to pick any k of the at most k of the items. Any k is fine, right? So so on a k uniform, how do I rate on this? Or maybe like I'll just speak. It's okay.
Sure. I'll try to figure out you can. Editing. I think we have to enable editing.
It's okay. I can just speak. Can we write? Yeah. Okay.
That's for eraser. 1%.
Oh, don't press. Oh, it's fine. Okay, fine. Looks like it's working. Let me just go ahead with the slides. Okay. So in this context, it's known that when your Metroid is k uniform, no, it's going ahead once again. K uniform. Pardon my handwriting. So it's known that you can actually achieve a competitive ratio of something like 1 minus constant over square root k. So apparently, as you allow more and more elements to be picked, you can basically afford to make more mistakes. So which is why the competitive ratio improves to 1 minus constant over square root k. So the open question is, so can we generalize this to Metroids? Can we identify one property of Metroid such that if that property is large, then you can actually improve the competitive ratio from half to something which goes towards 1. And I can tell you one such property. Is it the girth of the Metroid? So is it the set of the smallest, is it the size of the smallest infeasible set of the Metroid? Okay. So for k uniform Metroid, the girth is k plus 1. The size of the smallest infeasible set is k plus 1. So if we take an arbitrary metroid of girth k or k plus 1, can we achieve this kind of a bound? That is the open problem. A special case is, so the reason why this half is tight for a single choice is because you have two elements such that you cannot pick both of them together. As soon as you have two such elements in your metroid, half is going to be tight. So suppose your metroid doesn't have two such elements, which means the metroid doesn't have doesn't have a dependent set of size 2. Then can we ensure that can ensure a better competitive ratio than half? Yeah, thanks. That's all I wanted to make. Yeah. If you take two I see. Not sure. Firstly, I'm not sure where represent. But how are we going to attack the problem? I know. Kind of. It's known for birth, it's not for. So, you know that. Okay, so. It's unpublished. Okay, I'm saying.
You want something to write on?
Yeah, okay.
You can flip it around.
And yeah, since here are so many people interested in algorithms and uncertainty, let me advertise in a few minutes an uncertainty model which is not so well studied, I would say. I'm on this one. You cannot hear me. Can you hear me now? Should I repeat? No, good. So in most you broke it. Cool. Wonderful. So in the traditional uncertainty models, there's stochastic or online uncertainty or some variance. And typically we cannot really directly ask for more information. Of course, we explore while solving a problem, we find out the true values, but we cannot really actively make a query and get the precise data. And I call this explorable uncertainty, this area in which we actually want to model such problems. And let me make a very precise example. I want to talk about finding an MST in a model with stochastic explorable uncertainty. So let me give you a very small example. So let's say here I'm given a graph. And now for the edge weights, there's uncertainty. I don't know the precise edge weights, but I'm given intervals. So let's say, oops. So here I'm given some intervals, I don't know, maybe let's say this is just 2. So, yeah, sorry, this is, and maybe, no, let me say this is 0, and then this is 2 and 4, for example. Yeah, let me not put everywhere weights. So I'm given a weighted graph, but I don't see the precise weights. I have these uncertainty intervals, but I still want to identify the minimum spanning tree, the minimum cost spanning tree. I cannot find this out right now, right? Suppose here are more weights and I don't know. I need to make queries, and I can now make a query to an edge and ask what's the precise weight of this edge. And now this is an expensive process, this making queries, and I want to reduce the number of queries I need. Okay, so my goal is I want to use only a minimum number of queries to find out the true minimum cost spanning tree. Okay, now I can, so let's say in this example here, I mean, we see already this edge, let's forget about this part. Okay, let's make it a triangle, that's easy. MST on a triangle. We see that the 0 edge is certainly in this, no matter what the true value of the other 2 edges is, this will always be in the MST. But for the other 2 edges, I cannot decide, I can make a query. And let's say I query this edge, it could be that the result now is 2.5, then this doesn't help me anything, I still have to query the other edge. But an optimum solution maybe is lucky because it knows in advance that the true realization here is 4. And it would kick out this edge, and it knows the true MST. Yeah, so an adversary kind of sees in advance what the outcome would be and shows me or proves with a minimum number of queries what is the true MST. And this will be now my evaluation of performance for an algorithm. I check what's the number of queries that my algorithm does versus the optimal or the minimal number of queries. Oh, I cannot write here. Okay, it's kind of similar to a competitive ratio. This is my performance evaluation. And why do I do this? Why don't I just count edges? Nah, because I can come up with instances where you will have to query all edges. So you will not get results of the type you never need to query more than 2/3 of the edges or something. So what is known in an adversarial model, like I describe it here, in an adversarial model, you can show a competitive ratio of 2. So there's a 2 competitive algorithm, and this is best possible. Like this example actually shows you that you might need 2 queries, while an optimum needs 1 query. And the question now is, what if I don't look at this adversarial model, but I say the realization, so I draw this actual weight randomly from this interval, uniformly, or there is some underlying distribution and the algorithm might know it or it might not know it. So there are different flavors of this type of question, but the basic question is, assume the true weight comes uniformly at random from this given interval. Can you beat this factor of 2? That's a question. And of course, in this context, you come up with, can study all kinds of problems, matching problems and whatever other problems where some values or coefficients of the cost function are uncertain, and you want to solve the problem. Thank you.
So good. So I'm going to propose a question that, okay, so the question is the following. I'm trying to serve a bunch of customers. So these customers are sitting in some waiting room. Each of these customers has a value. I want to serve them. So here's what happens. I know the values of the customers. So I decide to choose a customer to serve. But the customer, so I'm serving this customer, I get their value. But the other customers are kind of impatient. So while I'm serving customer 1, every other customer pulls out a coin, flips it. If the coin comes up heads, they leave. I'm just choosing some model for how to model the impatience of the customers. The simplest model is like a geometric kind of model. Okay? So each customer has a coin whose bias represents how impatient they are. Okay? So maybe, I serve customer 1, but maybe customer 2 decided to leave. Customer 3 remained. So the next time step, I can serve customer 3. And if there are other customers, the same process is happening at each point in time. Is the problem clear? For simplicity, let's imagine that all the customers are known right up front. They're sitting in my waiting room in the morning. And I suppose I know their values, and I suppose I know their impatience probabilities. I'm just making the problem as simple as possible. Value is the profit I get. Value is the profit I get from serving the customer. I want to maximize the expected value, expected total value of served customers. Multiple customers can leave at the same time. There is no relationship between the values and the profits, between the values and the probabilities. So there could be very valuable customers who are total saints. So, if there's a valuable customer who's a total saint, you might decide to just, keep them around and serve them at the very end. So you could decide, there are various policies you can try to figure out based on the values and the probabilities. By the way, since you know the values and the probabilities, they're end customers, you can actually write a massive dynamic program. Much like Sahil was talking about a massive MDP, it's just a massive dynamic program. You can write it, its size is exponential in n, you can solve it. So it's a computational question. And so I'm asking for an efficient algorithm for this problem. And this is just one example of a kind of sort of a dynamic problem where the dynamics are now captured by a stochastic process. Okay. So what do I know about? Oh, I'm happy with approximations. So 2 is trivial. Each time you pick the person with the highest value. That's a factor 2. Okay. You can actually model this as some kind of vertex-weighted online matching problem, where one side is time, the other side is customers. You can do some tricks like that. You can get 1 minus 1 over E, the same 1 minus 1 over E that Steffi mentioned, but 63%. Okay, and that is compared to the hindsight optimum. But then you can start to approximate the best algorithm, the best, the expected value of the best policy. And I know how to get 70%. I don't know how to get better. This is a paper a few years back. It was a paper in the this is a paper in the ITCS conference. It's a paper called Catch 'em If You Can. If you catch me, I'll tell you the name of the paper as well. It's on my webpage. But I would love to understand questions like this. Questions where there's some dynamics that are happening, which are exogenous, which are not dependent on my own which are dependent on my own decisions, but in a sort of exogenous sort of way. Démalo. Exactly. So with respect to the hindsight optimum, no, with respect to the hindsight optimum, there is a computational issue out there. You're right. But I'm interested in comparing to the best algorithm, to the best policy. So I am looking at the value obtained by the best policy. the output of a dynamic program, which is, it's saying, well, if you have all these people, who's the person you should pick in the first step? And then so many people leave, and who should you pick in the next step, and so on and so forth. So it's a massive policy, basically. It's the expected value of this thing. Absolutely. Yes. Sure. It could be, you might be able to get 1 minus epsilon. I don't know of, yeah. Uh-huh. Oh, interesting. Basically, everybody should ask Sahil for whether their open problems have been solved or not. But so apparently in quasi-polynomial time, you can solve this problem. Okay. Okay. But in general, I would like to push this general set of questions where the process is evolving. So these are also known as restless bandit problems. Many of you might have seen bandit questions, where at each point in time, you pull an arm and you get some value. But these are known as restless bandit problems, where you pull an arm and you get some value, and the process evolves according to the arm that you pull. But every arm that you don't pull, it's kind of restless, and it moves of its own accord according to some other process. What can you say about these kind of restless problems? They capture all kinds of sort of interesting questions. If you can say, positive results, ideally, or negative results, at least put us out of our misery. Right? We know what we can't solve. Anyways, let me stop there unless there are questions. Maybe some other people will propose one more question. We have time.